determination of temperature coefficient of resistance, temperature coefficient of resistance of a wire. So here we are going to use the meter bridge and resistance blocks to find out the temperature coefficient of resistance of a wire. So the experimental setup is like this. We have the meter bridge. So this is the meter wire and the galvanometer setup with the higher resistance and a switch in parallel to it, and the jockey. So here we connect the resistance blocks. Let's connect the resistance box over here. And here we are going to connect the wire. So we want to change the temperature, right? To change the temperature, we need a setup to change temperature, and to measure the temperature, we need a separate setup. So that setup, for that setup, we use a beaker that is filled with paraffin wax. We avoid using water because water is conductor of heat. So what we are going to do is we are going to put this wire into the beaker. I'll draw it closer. So the wire is woven around a wooden coil. So here we have a wooden coil. Around that the wire is woven. And now we have filled this with liquid. We need a stirrer to mix this when I heat using a Bunsen burner. So from here I provide heat. To measure the temperature, we need a thermometer. To give away the heat uniformly, we use a wire mesh. Okay, so in this setup, first we set up this meter bridge. After that, we balance and obtain a reading L. Using that, I can find out what is the resistance of this. Next, I increase the temperature. And find what is the resistance. What is the resistance at that temperature? So theta and theta r. We put a table theta and theta r. So for given temperature, what is the resistance? We find that. Once we have found, we can plot a graph. Now we know the relationship between r theta and theta. That is r theta is equal r naught 1 plus alpha theta. So now we can get a relationship that r theta is equal r naught alpha theta plus r naught. So using the graph, we can using this table, we can plot the data points. Using the data points, I must be able to draw a graph. Using the graph, and the intercept is going to give us the value of r naught. The gradient will give r naught alpha. So from the intercept, we found what is r naught. Then when you divide the gradient by intercept, you get alpha. Okay. Is the experiment in short clear? The idea of the experiment. Sarah, how about you? The idea of the experiment is clear what we do here and how we are going to find what is alpha. Draw the setup. Draw the setup and below write so here why did we use a resistance box without using a rheostat? So here the uh, equation during balance will look like this. Okay, from the resistance box from the resistance box, use a suitable value. So we're going to keep the balance length between 30 and 70 centimeters. So r theta over r, let's say this is rb. rb is equal L minus 100 over L. L minus 100 over L. So r theta is equal L 100 minus L into RB. Now, this is the first point. Look, do we need the value of r theta? Do we need the value of r theta? We need to find the value of r theta. To find the value of r theta, the value of RB is necessary. So here, if I use a rheostat, can I get the value of RB? No. Therefore, only a resistance box is suitable. Okay. A rheostat cannot be used for this experiment. So I will turn this setup. Okay, note and let me know. Sarah, okay, have you noted this note also on the side? I mean, the procedure. Okay, and we also know that, but r theta is equal r naught 1 plus alpha theta. So here r theta is equal r naught alpha theta plus r naught. So this is in the form y is equal to mx plus c. Okay, so what we do is when paraffin is heated, the value of r theta is found for every rise of 10 degrees Celsius. So, comma, then r theta versus theta graph is plot using the data. So when we plot r theta, r theta versus theta graph from the data points, we will be getting a y equal mx plus c graph. So these are the data points. So from the data points, we get a y equal mx plus c graph. Here, this intercept is equal to r naught, and let's say that is c. Here the gradient. So when we are finding the gradient, we take two points that are not data points, okay? And find the gradient theta. So C is equal to R naught. M is equal to R naught alpha. So alpha is equal M over C. Okay, alpha is equal M over C. Hence alpha is determined. Alpha is determined. Below that, let's write a note. Note number 1. Instead of water, paraffin is used. Paraffin is used due to the following. Due to the following reasons. First, safety. First, safety. Paraffin is an insulator. Is an insulator. Paraffin is an insulator of electricity. Second, temperature boiling point is high. Boiling point is high. Therefore, range of temperature is high. Therefore, range of temperature is high. Second, heat is produced inside the wire. It's produced inside or produced in the middle. Produced inside the wire. Inside the wire. Therefore, the surface temperature of wire and core may be different. This can be minimized. This can be minimized. By using a thin wire. Next, now here, when you have a very small portion of the wire, Why did we make a coil here? What is the purpose of this coil? We could have used a single piece of wire like this, right? Inside the liquid. In that case, this length is low. Therefore, the resistance of this part is not significant. When we make a coil, like this, now it has more length inside water, therefore the resistance is significant. We can make it a better version of this like this. We can take a coil. We can make a wooden coil like this. For better results or for better accuracy, the core the coil can be prepared as follows. So you can take a wooden core. You can take a wooden core and this is the wire. Bend it into two, and now wind around this coil. So when you do this way, now you can increase the length of the wire. Therefore, the accuracy of the reading will increase. Okay. The wire is bent into double thread and woven around the wooden core. Both of you, are you clear? Noted. Sir answered, okay, I will note it. Shall I move to the next part? Next topic, potentiometer. So we were discussing about the application, right? There were two applications of Wheatstone bridge. One was the meter bridge, and now the second one, the potentiometer. Potentiometer. So what is a potentiometer? Potentiometer is a potential divider. Used to measure EMF and potential difference. And potential difference. So let's say this is the normal or the simplest diagram for a potentiometer. We have a battery. So we call this one as the primary circuit. We know if the EMF of this battery is E, then let's neglect the potential drop in these wires or in these thick connectors. Then the potential, this entire potential will drop across this battery. Sorry, across this wire. Okay, the entire potential will drop across this wire. Now we have another secondary circuit. In this secondary circuit, let's say the EMF of the battery. Now this battery has an internal resistance also. Here we have a galvanometer, and let's say this battery has an EMF of E naught. Now, if the drop, now anyways there will be a drop in this wire, right? Let's say this has a drop of V. If E naught is greater than, if E naught is greater than V, then look, in this path, will there be a current flow? If E naught is greater than V, there will be a current flow. Galvanometer deflects. Galvanometer deflects. Say in this direction. Let's say the galvanometer deflects in this direction. This is a center zero galvanometer. Center zero. The same setup. The same setup. But this time E naught is equal. E naught is equal to V. E naught is equal to V. If E naught is equal to V, galvanometer has no deflection. Has no deflection. Because there won't be a current flow in the secondary circuit, okay? Not the primary, in the secondary. And then we have one more case where V may be greater than E naught, right? E naught is less than V. That means the current will flow in the opposite sense. The current will be flowing in this direction. Here there is no current. Here it will flow in the opposite sense. Then galvanometer deflects, but the deflection will be in the opposite direction. So now you should have understood that using a using a potentiometer, you can measure the EMF of a battery. Look here, when there is no current flow, or when there is no deviation, when there is no deviation, these two are balanced. That means their potentials are same. If we can measure this voltage, then we can find what is E naught. So the rough idea about about potentiometer. Did both of you get the idea? A rough idea on how the potentiometer works. draw these three diagrams, and once you have completed, let me know. Sarah, not ready. So look at the deflections. Deflection is also important. Here it's on one side, here it's on the opposite side. So let's redraw the potentiometer. Just like just like the meter bridge, here also we have a quite similar setup. We have thick connectors, so we can neglect the potential drop across those connectors because the resistance is low. So these are thick connectors. Here also we have a wire of length 1 meter. There are even lengths that are greater than 1 meter. Let's discuss that later, how we can increase the length. So usually it's 1 meter. So we call this circuit is the primary circuit. This is the primary circuit, and let's say this is E naught. This is the plug key. This is a plug key. And now we have our secondary circuit. Now secondary circuit. We have the galvanometer and a setup to protect the galvanometer, a higher resistance setup to protect the galvanometer, and the jockey or sliding key or the contact key. And we call this circuit a secondary circuit. In meter bridge, we only had one circuit. Here we have two circuits. That's special about this. So this battery has EMF E, and it also has internal resistance R. Here also you might have internal resistance. That doesn't matter much. And here is a higher resistance. So here, this wire, let's say wire AB, wire AB the uniform wire AB is made of nichrome or manganese, just like the meter bridge, nichrome or manganese. So what might be the reason? Because they have very low temperature coefficient. With temperature, their resistance doesn't change much. When the resistance doesn't change much, then the potential drop is also constant across it. So here we have two circuits on the potentiometer wire. Two circuits are made on the potentiometer wire. On the potentiometer wire. They are known as the primary circuit, the primary and secondary circuits. Next, the state when no current passes through the galvanometer when sliding the key along the wire is called the balance condition. This point